Okay, welcome to the New Mexico Museum of Natural History and Science virtually, and to our continued celebration of the landing of the Mars Perseverance rover. According to my Mars watch here, it is getting close to 7 p.m. Mars local time at the landing site. And as you all know, Perseverance landed a few hours ago, safe and sound. We are very proud to be one of only 2 museums nationwide with a direct connection to this mission. And the other is the Smithsonian Air and Space. So we like to say they're in good company. While I'm remembering, please remember to check the museum website for our Perseverance page of activities, information, links to NASA websites, lots more information about the mission. And we'll be adding to that as the mission proceeds. For today, I have a couple of quick things to tell you. There will be time for Q&A after the talk. Please enter any questions you might have during the talk or during the Q&A session into the Q&A box, not the chat box. We'll keep track of them. Some of them might be answered right away in the Q&A box, so check on your question periodically. Others will be forwarded to Larry Crumpler to answer at the end of the talk. There is a survey at the end of the talk. We would greatly appreciate it if you would take a few seconds to fill it out and click on it before you leave the webinar. This talk is being recorded, and it is also simulcast on YouTube. So for those of you watching on YouTube, we want to remind you that you have to register for the Zoom webinar in order to ask questions. And you can do that anytime during the talk. The link is on the museum's website and Facebook page, and it's also on the first screen. So if I could ask Larry to start sharing his screen with us, okay. You'll be able to see it.
I think the host does this. Oh, there we go. Maybe. Okay, let's see.
For those of you on Zoom, you might want to reduce the photos of the speaker's host. And if you haven't done that before, you can go to side-by-side gallery.
The host needs the, there we
Jim,
go.
Can you release it so that Larry can share his screen?
Got it.
All right, great. All right, there is the link for this Zoom webinar for those of you on YouTube who might want to ask questions. All right. If you do want to activate your computer's closed captioning, click on the live transcript menu at the bottom of your screen. This is the final of the 3 events we're offering this week, but we'll be having more in the future as the mission proceeds. So do keep an eye out for future Perseverance webinars, talks, events of all kinds. Now, one thing that's happened recently is that this has become a very popular event, the Perseverance landing. And there's all kinds of really cool pop culture items. So I can show you one here if Jim gives me back my video.
There you go.
There you go. This is a Mars dust globe. And on one side, you've got a beautiful hemisphere showing Valles Marineris and the volcanoes. On the other side, you've got a very nice cross section and two astronauts. And if you turn it into a dust storm, it's a very nice model. It takes several hours to dissipate and settle. So think about Mars. And Jim Greenhouse, our space science director, has some other really cool pop culture items that we wanted to share with you.
I have two to show you quickly. One of them is, I hope I can go full, I will go full screen here in a second. Maybe I will, maybe I won't.
Yep, you are.
Okay, so here is a Hot Wheels, which makes the little cars that you used to play with when you were a kid. They actually made a Perseverance Rover model. So you can see it says Perseverance Rover right there on the bottom. And I'm like one of those people who, with the collectibles, who doesn't want to take it out of the package, but eventually I will take it out of the package. I just thought it looked better the way it was in the package today. And then museum staff and some other folks got to enjoy Mars donuts. So Krispy Kreme today only had Mars donuts available this morning. And I'm wondering if Larry can tell us why only part of Mars is covered with chocolate sprinkles and not the rest of Mars. Maybe you can tell us that, clear that up for us here in just a moment. So there's a couple of the fun popular cultural things that were happening today to celebrate the landing of Perseverance. Thank you, Jane.
Okay. So Larry, if we can get back to screen sharing and go to the next slide, it is my privilege and pleasure to introduce our speaker, our Perseverance scientist. Dr. Larry Crumpler is a research scientist at the museum specializing in volcanology and space science. His PhD in planetary science is from the University of Arizona, master's in geology, University of New Mexico. Prior to the museum, he worked as a researcher on the staff at Brown University. He's published lots of professional papers, book chapters, geologic maps, and is just completing a book about Mars that will be published at the end of this year. So keep an eye out for it. He's a fellow of the Geological Society of America. His role on the mission will be to produce geologic context maps of the terrain traversed by the rover. He's been a team member on several other Mars missions and previously participated in other NASA and Russian missions. So, with no further ado, please join me in welcoming Dr. Larry Crumpler. Larry, take it away.
Thank you. So we made it to Mars, right?
Woohoo!
It's those last, several minutes that are the real killers. I mean, because every step of the way, there's a showstopper, and you get past one, and then you got to get past the next one, and then you finally get that last call. So we're there, and so we're ready to go. So let's talk a little bit about where we went and what we're doing. Okay, so this is a northern hemisphere of Mars. So we're not quite going very far below the equator, all the way up to the North Pole, and it's on the what we call the eastern hemisphere. And the yellow dot shows where we landed. It's Perseverance crater. It's on the northwest corner of a place called Isidis Planitia, and Isidis Planitia is not quite 1,000 kilometers across. So it's a big basin, and we're in sort of the rugged mountains on the northwest corner there. And a couple of other things, we're sort of in the company of some other landers on this hemisphere. over on the right, just above the scale bar there, you can see there's where the Chinese lander and rover is going to land later this spring, hopefully. At least that's the current projection for where they think they would like to go. And then a little bit further over to the right, of course, is another white dot. That is the U.S. InSight lander, the one that took a seismograph to Mars so that we can actually understand the interior structure of Mars, and so that's active. And then below that is the Curiosity rover, which landed in the Gale crater back in 2012, and it's still active. So this is going to be an active side of the planet here. So let's talk a little bit about the actual landing site. So this image shows in the upper left an image of the Jezero crater. That's the target. And it's about 48 kilometers or about 29 miles across. And so the lower left, you can see a Landsat image of Albuquerque and surroundings at the same scale. So Jezero crater would encompass everything from the East Mountains out to the just about the Rio Hueco over to the west of Albuquerque. So it's a big area, and in it there's this interesting thing you can see in the upper left image again. There's a channel that comes into the crater, and where it enters the channel, it deposited a beautiful delta. Deltas happen when water enters a river enters a large body of water like a lake that we believe filled Jezero crater 3.8 billion years ago, and deposit sediment. So a good example would be, of course, the Mississippi River Delta and the Gulf of Mexico, and of course the Nile River Delta. So that box then is expanded over on the right side of the slide here, and you're looking at the area of the landing ellipse shown by the circle, and that's where we expected to land with a better than 90% probability today. And of course, the color coding is elevation, so the bluish, greenish tones are lower, and the reddish and the whitish tones are high. So that's the rim of Jezero crater on the left, where the channel enters. So the idea was to visit this delta on Mars. So here's the final results. This is where we actually landed today. So the original desire was to land a little bit closer to the delta up there, but we went a little bit long. And that's okay, because there's a couple of interesting geologic units out there in the crater floor that we actually have to cross. So I'm rather pleased with this location. So we can zoom in a little bit to see what the terrain looks like around that yellow dot where we landed this afternoon. And this is a little bit better view. So you can see we're sitting in this unit that has the kind of a lot of small impact craters. And then to the left, there's a contact with some other unit that has this sort of, I don't know, fabric or grain or texture that's kind of lines going to the upper right and lower left across this kind of a corrugated terrain. Be interesting to see what those materials are. And then in order to get to the delta, which is in the upper left corner of this slide, we'll have to cross that and go across a smooth terrain, which if you look at in detail, actually turns out to be kind of highly fractured. So that could be, who knows, some sort of fine-grained sediments or something. So anyway, let's zoom in a little bit closer and see where we are. So this is what it looks like in our near vicinity. So there's a 50-meter scale bar. And so it's kind of an interesting place. There are some strange polygonal outcrops off to the east, to the right. And then, of course, there's a series of dunes that we would have to traverse over there on the left in order to go out of this image out to the north. So we now have a couple of Cam images. Those are the low resolution images taken out of the front and the back of the rover just after landing. And so we can look at what this terrain looks like from the ground now. And so this is just a view of perspective, so you can see where we've got to go in order to get to the delta. So there's the first Cam that you probably saw if you were watching the coverage today. This is, of course, this is a low quality, quick grab image. There's still a kind of a lens cover over the actual camera lens, and there's a lot of dust on it from settling out from the landing operation. So it's a little bit fuzzy, but that's what we're sitting in. So it's a fairly benign terrain, a few rocks scattered around, a lot of loose soils. And someone suggested that kind of thing on the horizon off to the very top of the image might be the delta itself in the distance. We'll see what happens. Over on the right is the or the left rear wheel of the rover. So this is the right eye of two eyes of the rear HazCam. And another one you may not have seen is that there was a front HazCam image, but it was only a partial image before the transmission was shut off for today. And so you're looking at just the top of the HazCam image there. And of course, the transmission shut off and sort of resulted in that large square dark area on the right. But again, fairly benign terrain. There's some rocks out towards probably those polygonal outcrops that we saw out to our east. And we'll get a better view of these as more data comes down in the coming day or so. So what happens after we've landed now? So basically from now through Monday or so, we'll be doing a lot of deployments of instruments like the main camera mast and the high gain antenna. A lot of other things. We'll be checking out some what we call liveness checks of instruments and equipment on the rover. And we're actually going to have some science team meetings coming up beginning today and through Monday, which we'll be discussing as the data comes in, some of the geologic characteristics. So we'll be all kind of busy. In fact, there's a first science team meeting is about 9 o'clock our time tonight. Then through the next week or so, towards the next week, we'll basically be transitioning to the surface operation software. So we're operating on the entry, descent, and landing or cruise stage software right now. So it's a whole different set of abilities for the rover. So we'll be doing that, setting those up. Then we'll be, beyond next week, we'll be checking out all the remote sensing instruments. And we will eventually unstow the large arm on the front and maybe check out a couple of the instruments and probably try to do an initial drive to check out the mobility, as we call it, the ability to move around. And somewhere after the next 2 weeks, and maybe a little bit sooner if everything goes well, we'll actually start doing some science on the local surface just as a first test, but we'll also drop the helicopter that we've taken along, which is one of our technology demonstrations, is stored in a little package on the bottom of the rover. And so we'll drop that dust cover off of that, which was there to protect it from all of the rocks and pebbles being thrown up during the rocket landing. And we'll unstow the helicopter and drop it to the ground and probably drive away and then probably do those tests sometime within the next month or so, if we're lucky. If not, it'll be certainly within the next 60 days. So that's kind of the plan. So that's what you can expect. So you'll expect on your end, you'll be seeing more and more interesting images. We'll probably take a Nav Cam panorama at some point. And then we'll start once we start checking out some of the other instruments, we'll get some of the nice color images and high resolution things going. So again, getting back to the helicopter, there in the upper left is what the helicopter looks like relative to scale. And above it on the front of the rover there, you can see a few little circles at the bottom of the rover body. It looks like the front face of a car radio or something. Those are actually little cameras. There's actually 4 of them. Those are the HazCams. So that's what you were looking out of in those first landing images. So the helicopter again has rotors that are about not quite 4 feet across. So, and that's of course because it's in a very thin atmosphere of 1/100th of the Earth's atmosphere, and they have to spin a couple of thousand RPMs in order to sustain lift in that thin atmosphere. Nonetheless, it's been tested in a vacuum chamber or a Mars atmosphere chamber, and it is capable of lift and actually being commanded up and down and around in that environment. Over on the right is where we landed, and the lavender areas are places that we predetermined are places where we could operate the helicopter if we wanted to. And if we landed off of one of those, we would drive to one of those in order to deploy the helicopter because it's a fairly flat and benign area. And we landed right in one of those very, very smooth areas. So probably what we're going to do is probably drop the helicopter right here, I should imagine, and then maybe drive north, maybe 100 meters or so, stand off, and then have the helicopter do its thing from this location. So it'll be kind of interesting to see what we all decide to do over the next few days. But that looks pretty realistic to me. The helicopter flight plan will be a few flights, doing increasingly more complicated things, flying out and back eventually, and then we'll see where we are at that point and go from there. Just a quick review, the goals of the mission, of course, are these 4 basic goals. We want to understand the geology and get a good handle on the region's geologic history, because we're there to do an astrobiology science experiment. That is, we want to look at the rocks and determine if there was any viable organic compounds in the past. And we'll do that by looking and checking for the presence of organic compounds, and if we see something really interesting, we'll probably cache that sample on the surface for a later return, which is the goal in the upper right there. That's we're going to be doing sample caching. We have a good 38 samples that we can actually collect, and we'll probably collect about 20 of those early in the mission, and we'll store them in a place on the surface for later return later in the decade by a retrieval rover. And of course, the whole thing also has a lot of technology that we're testing for the presence of humans in the future that would be both able to sustain the presence of humans on Mars, as well as some of the activities that humans might need to do on Mars in the future. So, series of goals. The rover itself, of course, looks like Curiosity, the previous rover, but it's vastly different. It has the basic design is that of Curiosity, but it's a heavier rover. It has a whole different suite of instruments, and of course, it has a new main camera, the Nav Cams, which that's the one that takes all the color images that we'll see. That will make beautiful views of the scenery. Also, it's a multispectral camera, so we'll be doing a lot of science with that. Then there's SuperCam, which was the instrument developed by Roger Wiens and co-investigator Hort Newsom at UNM, and Roger is at LANL. That's the laser shooter that shoots rocks and then analyzes the cloud of debris, the hot debris, from that laser shot spectrally to determine all sorts of things about the chemical composition and the presence even of organic compounds in the outcrop that it shoots. And then we have a bunch of instruments on the end of the arm, the thing that looks like a big club there. Sherlock is able to identify at the micro scale organic molecules. And it also has a microscopic camera. And then Pixel is the thing that will tell us what the actual elemental composition of the surface materials are at, again, micro scales. And then there are a couple of other instruments. RIMFAX is a ground penetrating radar as the rover drives along. It continuously does subsurface radar penetration with subsurface estimates of density variation, so we'll get kind of a cross-section underneath the rover as we drive along. MOXIE is the one of the technology demonstrations that will attempt to do extract oxygen from the carbon dioxide atmosphere for future human presence on Mars purposes, as well as making rocket fuel in the future. And of course, then Ingenuity, which is the name for the small helicopter. And the whole mission is totally different in that we're really mean, lean, fast traveling machine. In this case, we're not just going to hover around outcrops for weeks and weeks. We've got a kind of a series of goals we've got to accomplish, mainly collecting samples, 20 of them, very quickly, probably in the next year or two, that we can leave on the surface for retrieval by a later rover. So that means faster traverses and a lot more quicker activities. So we've implemented a lot of activities with the actual control of the rover to effect that rapid transition, including longer work days, unfortunately. So anyway, the traverse would look something like this. And of course, we landed a little bit off the very, very, very bottom edge of this image here. So we'll have to cross that rugged looking area there near that little crater to get to the green line. And we'll probably follow some traverse that looks like this up onto the delta that you can see sort of spread out there. The delta, of course, has seen some erosion, so it's going to be a beautiful layer cake, northwestern New Mexico type of landscape. So you have that to look forward to. And then we'll be traversing up the delta towards its entry into the crater up there, where the slope goes up about 1,000 meters onto the surrounding highlands. And right there where it does that long traverse along the margin of the channel, there's a lot of carbonates detected from orbit. So we suspect that was an ancient shoreline. And the big question is, what are those carbonates? Are they typical inorganic carbonate depositions, or are they something else? We'll find out. And of course, the delta is this sort of thing. This is an Earth-type delta, of course. And again, what this is all about. It's sediment being brought down by a river. It gets, enters water. The flow of water slows down. It drops everything out. So you get these beautiful, nicely laid down sequence of sediments, and it just builds out into the ocean. So you get this uniform sequence of materials, and everything's buried rapidly, and so everything's preserved. So it's a beautiful place for going and looking for preservation of something that you are looking for that may have been deposited by these sediments. And getting back to the sample return, so what we're going to do is we're going to collect these into these little tubes inside the drill bit, and we take them out and we store them on the rover, and then at some point we'll take them all out, or at least a batch of them, a cache, and put them on the surface. They're designed to be protected in the environment on Mars, right on the surface. And then number two, later in the decade, probably 2026 or beyond, we'll send a retrieval rover, which is designed to actually retrieve those. And then three, return those to an ascent vehicle where they will be sent into orbit to rendezvous with an Earth return orbiter, and we'll get those samples back on Earth. At least a good sample of 20 or so, or if not more, samples. So what am I going to be doing on the mission? A lot of words here, but the bottom line is I'm going to be doing field geologic mapping. I had a lot of success on the Mars exploration rover, taking the process that we do here on the Earth to actually do geologic mapping in the field on the Earth to the rovers, because they have many of the same characteristics. They look at the landscape, they look at rocks, they're able to actually put those in the location on a map as you drive along. So I will be keeping continuous geologic map along the traverse, and I'll be making a cross section with that to compare with the RIMFAX, or ground penetrating radar. And the whole goal, of course, is to really lay down a good documentation for all of those samples that we're collecting. One of the goals of this whole sample return thing was to actually make sure that we did what we call preemptive documentation. Collect all the information you could possibly ever hope to need. And one of the things that was kind of left off when a lot of the mission or early planning was the field geologic mapping. And so I made sure that got on there. And of course, again, even the mapping itself that I'm proposing is going to be something that we can develop for the future robotic missions, as well as though likely to fall into the venue of what humans can do on the surface of the planet as they drive along. They won't be able to walk across the surface a lot, but they will be able to do this sort of geologic records. So just an example of what one of those geologic maps will look like from one station. So there's an increasing series of levels, or actually decreasing in quality levels, with the highest level being the closest in level 5. And I will keep this information at each of the sites as we move along. So we'll have a continuous strip map populated with all of the information that geologists do, like the attitude of units. We'll have images, we'll have sample locations, all of that located within this map. And of course, then we can compare it with what we're seeing with the RIMFAX ground penetrating radar along the dashed line there, along the Rover's traverse. And so they'll all make a nice a package for the mission. So just getting back to our landing site, just thought this was kind of interesting. I did a test example of what one of those maps might look like on our high-rise orbital image. And long ago, I selected this area because I thought that it was kind of close to where we might land. And sure enough, there's the actual landing location today, the yellow dot. So I literally put the map only 90 meters away from where we eventually ended up landing. So that was almost a hole in one thing. Okay, so and don't forget there are a couple of other people in the state of New Mexico who are involved in it. Of course, Roger Weens, the principal investigator of SuperCam, and Horton Newsom up there at UNM, who is the co-investigator for SuperCam, and also on MSL. So with that, I will stop and take questions.
All right. And boy, we've got a bunch of them too. So let's get started. The first, okay. The first question is, what is your most wanted sample in or around the crater that the rover might cache?
Yeah, the most wanted sample would be the, of course, the something with organic compounds in it. And so that would be, a rock that probably had some sort of evidence for some sort of something other than the typical minerals that we see in any rock in a semi-arid setting. And if we saw organic compounds in a rock and it was in a layer that we thought was deposited by water, for instance, or had some other things that are morphologically associated with past life, we would certainly want to collect that. And that's probably going to be the sort of the thing that we'll be looking for at a lot of those places. But there are other things too. One of the things we hope to get are, pristine samples of some of the rock types that make up some of the big geologic units that we see here, so that we can bring those back and date them, and finally start talking about putting real age ranges on some of the events in Martian geologic history. So those are two competing goals there, but those are the two big ones that we would like to see.
Okay. There are two questions that kind of work together. When did you guys start planning out Perseverance? And how long did it take to build Perseverance and Ingenuity?
Oh, gee. The building of the whole rover was a good decade at least. And that started almost immediately as soon as the Curiosity landed in 2012. So it's been going on since then. We knew all the things that we wanted to do, and we started planning those. And Ingenuity was kind of interesting. It kind of came along in the second half of that process. And a bunch of us actually proposed that as an instrument for this mission, to drive along and actually provide, kind of, a scouting capability for the rover. And that instrument was not selected in the initial selection of series of instruments to go on it. So, but nonetheless, there were a number of high-level people in NASA who thought that it would be useful enough to actually do that experiment that should go on. So then it had to be accommodated in all the plans at the very end. That made a lot of engineers at JPL unhappy, but it made a lot of us happy. And anyway, it made it onto the rover, and by hanging onto the belly pan, and hopefully in a couple of weeks we'll get to test that out.
And what's the timeline for a mission like this? When did planning actually start?
Well, yeah, well, for the, as I said, for this particular mission, it was actually 2012. And as soon as we landed, we started, designing the template for what we wanted to do. So, and of course, the actual planning for the Curiosity, which was kind of the basis for the actual rover, the mobility as we call it, was a decade and a half before that. So yeah, I mean, it's all sort of a continuum of activity that ultimately results in an active mission.
Okay. This is also a multi-part question. I'll give you the first one first. Do you think that the rock specimens collected will show a history of climate change on Mars?
Yeah, well, the rock specimens collected show a history. Yeah, in the sense that we're going to collect rocks that actually do, in fact, preserve the sediments deposited by the delta. And so that will, address, what some of the um, water conditions were like at the time that the delta was being deposited. So that'll tell us a little bit about, the characteristics of the water, the how long it was there, and that sort of thing. So we'll start getting at that. But if we start climbing up the delta, we'll start seeing, the history of deposition associated with that river. And so that will certainly tell us if there was any changes, for instance, in the chemistry of the alteration of the rocks with time. For instance, the rocks got redder as we went up the sequence. It would say something about, the oxidation of the source area and so on. So you can bet that we'll extract every bit of climate history that we can from that series of sediments.
And the second part is, do you think this knowledge will be helpful in understanding Earth's geologic timeline and our future?
Yeah, well, one of the ideas is that we are really interested in understanding how, for instance, life got started on the Earth, and we kind of don't have a lot of record about that particular time period on the Earth. There's not a lot of exposures about that. So this is a planet where the entire surface is practically that age. I mean, at least the interesting stuff, the time when there was a lot of water. So we'll learn a lot about how the early processes might have worked at that time, because Mars and Earth were very similar early in the Earth's history. So by and large, the exploration of the planets in general have told us a lot about the early history of the Earth, because they preserve that time period in the solar system when the Earth was so active and subsequently has destroyed much of that record. So we're learning about Earth all the time, every time we go to one of these planets. And so Mars is going to be, it's just, sort of that intermediate sort of level of development, so that we're really going to learn about a lot of the time period before the time that we all know about. We all know about, the time period of after life got a foothold on land, and there's a lot of fossil record. But before that, a billion years ago and beyond, the record is a lot skimpier. So this is just perfect planet to understand that early phase of a planetary history.
Okay. So there's a complication here. The delta is in a large crater, but there are also some smaller craters that appear to be on the delta. So what's the timeline involved here? And how could that potentially affect biological activity?
Yeah, well, yeah. So we think that there was like a lake, like 3.8, and then sometime quickly after that, maybe
3.8 billion years.
3.8 billion. Yeah, sorry, yeah,
Yes.
and sometime rapidly after that, to say certainly less than 100 million years, it became a dry lake bed, and so somewhere in there we probably got the impact craters on the crater floor. And clearly, the impact crater on the delta was one of after the delta had formed. So we'll probably get a sense of the relative ages between the two, and if we get samples, we can actually tell you exactly when that happened. So we're probably talking about a time period of at least a couple 100 million years for the formation of some of the big craters that we see. And then there's been a lot of small ones ever since that time. But the bottom line is that the delta itself has been eroded somewhere over geologic time. It's not all there now. It's actually been eroded back. So that's why it has those steep margins, because real delta actually has these broad, sort of long, sloping ends or termini. And so if we can get a sense of the relative age between some of the impact craters and the actual modern day terrain at the edge of the delta, then that'll we'll be on our on the road to actually starting to talk about the how long we're talking about. So yeah, that's why it's going to be very fun to get some samples and get some dates, because then we can really pull that sequence apart totally in detail.
Okay. So 20 years ago, you advocated landing rovers in Isidis. How do you feel about being so close now?
Yeah, well, yeah, it's the thing about Isidis was that the terrain. I proposed a landing site very on the very south end of Isidis, and the terrain around Isidis Basin is some of the oldest terrain on Mars. So that gives you an idea of why this is kind of interesting to have this interesting river delta there. It's basically from really the early time of Mars, some of the earliest stuff preserved. So yeah, it's nice. That was kind of an interesting area to the south. I thought it was. I think it's even older in terms of the relative ages, so that might have been kind of really kind of exotic. But yeah, it's kind of nice. Wish we could have done it with one of the Mars exploration rovers, though.
And by the way, I apologize to you if you can hear a cat in the background. I could think she wants to go to Mars too, or she at least wants to join the conversation. And someone who is attending is part of the conversation. Dr. Hort Newsom from UNM is with us, who is also associated with the rover mission and with Curiosity. And he is asking if you could compare the advantages of the Perseverance cameras to the Spirit and Opportunity cameras.
Cameras?
Yeah.
Cameras. Oh,
Cameras.
yeah. Well,
sorry.
Yeah. Yeah, well, I mean, just starting out with the Nav Cams. Those are the basic ones, the black and white ones that take the beautiful, 360 panoramas everywhere we go. Those have like the ones on Perseverance have twice the resolution of the Spirit and Opportunity Nav Cams, and even twice the resolution of the Curiosity Nav Cams. And they also have color capability too. So those will be fun to play with on Mars. And then, of course, the Mastcam Z, which is the big panoramic color camera that sits on top of the mast. It has a zoom capability, so it'll be like going into the field not only with your nice phone camera and taking nice panoramic pictures, but it also has the ability to do telephoto. So you can really zoom really closely into something, or you can just do a nice panorama. So it's just the imaging capability is just awesome. So you'll see a lot of stuff, and the cat here wants to go to Mars for sure. He thinks it's a great camera. So.
Can the batteries on the helicopter be recharged?
Yes, I mean, it's solar powered. And actually, if you look at the image of it, it actually has these little square above the rotors, and it's actually a solar panel. So it recharges batteries in between flights. I don't know, I forgot what it flies for. What was it? It was like 40 seconds or something?
90 seconds.
90 seconds, yeah.
90.
Yeah, so it's typical, drone. You can't fly for very long before you have to recharge the batteries. But yes, we can, and if we're lucky, it'll last longer than the limited test. We haven't really talked about exactly what happens after that, whether it kind of flies along behind us or what. But we'll find out, maybe, hopefully.
And that is another question. Is Ingenuity going to be reconvening with the rover after its flights?
Yeah.
Or will it strike off on its own?
Yeah, we'll probably never go far from the rover, but we have to stay at least 100 meters away. There's a no-fly zone for the helicopter of 100 meters out from the lander because we don't want like crashing into it or anything like that. So yes, it'll if it stays alive past the test, I'm sure we'll really experiment with it and do things that we hadn't planned on doing, like flying out in front and checking out some terrain or something. I don't know. It'll be interesting to see how that whole thing goes. I mean, a lot of these test cases actually turn out to be even more useful than we thought they would. And we'll want to keep it around as long as we can.
So, and you may have touched on this, the expected range of the helicopter.
Yeah, well, the test suggests that if we really get ambitious, we might do a fly out 100 meters beyond the so-called airfield and come back or something. But I'm sure that we'll find what the capabilities are as we play around with the helicopter and do a variety of tests. But it certainly can go 100 meters. And when we were designing it, we were talking about flying out 1 kilometer and back or so.
So back to the rover, how fast can it go?
Yeah, the rovers are, they basically move like we've often said, the speed of a Galapagos tortoise. It's not really traversing. However, with this rover, we've got the capability of going pretty far in one saw, so it can kind of be like a really fast tortoise, maybe going several hundred meters in one day's drive, which would be couple of hours or something. So a very, very slow walk.
Okay. Some things about the delta itself. It appears we landed in a non-delta deposit some distance from the delta. Is that an issue?
No, I don't think so. I mean, there's a lot of debate about what the crater floor deposits are. One area of speculation is that it's old lava flows that filled in the crater. There's a significant volcanic province out to the west called Syrtis Major. And those flows are very fluid and went a long ways, and they filled a lot of things. So it's possible that some of those flows, filled in the floor of the Jezero crater, maybe even after the lake bed was there. So that's one idea. The other is that that could be airfall materials, that is volcanic ash from either that volcanic area or from one of the other global events of volcanism, or even the global impact cratering fallout. So it could be that sort of deposits. And of course, it could be just the sediments from the lake bed itself. And so it'll be interesting to find out what that is. And clearly, we have to cross that rougher looking area, so and that's kind of strange. And it looks to be maybe older than whatever we're sitting on. So that could be like an earlier part of the delta, and the delta has been eroded back a kilometer from that location. So that could be early lower delta deposits. You can't tell things from orbit. You have to look at them. That's why we send robotic geologists to the surface. So I can guarantee that it'll be very interesting to determine what those rocks are, and it'll be something that will make the story even more interesting than we think it is now.
And how long did it take to form the delta? Was it formed from some catastrophic flooding event or truly a river?
Yeah, we don't know. So we can kind of maybe poke around at estimating that based on looking at the geology, seeing if things change radically, if there's some reason to believe that that the topmost sediments are deposited way later, than the earliest stuff. But that's what we don't know, and that's why we would like to have true age dates on that. Yeah, and of course, the delta could have been some fairly rapid event, but the way it it has all those little snaking channels that diverge and flow across the top of the delta. Those are very typical of the type of environment on the Earth, deltas, where they enter a body of water, and from year to year, the channel takes a slightly different direction. So it looks like there was things going on over a long period of time, at least, not one big rushing event. So it was a fairly long-lived Martian river. But the question is, what is long and Martian time? We don't know.
So if you were to look at either the Nile or Mississippi Delta, assuming the same sort of erosion and history, where would be the most likely places for biological or microbiological traces to survive?
Yeah, well, the interesting thing is that things get preserved best in the deposits that are very gently laid down, as opposed to the rushing rivers and the really sandy river bottom situations. So a bunch of us think the best place to look for organic compounds are those very bottommost sediments. It's called the bottom set beds. And they get deposited in advance of the main delta as the river enters the body of water. The sand drops out of suspension really quickly, but a lot of the really fine silty stuff kind of goes way out into the lake or the sea, and then settles down gradually and results in this sort of really muddy, clay-rich, finely deposited, finely laminated material out there called the bottom set beds. And boy, if you wanted to find some well-preserved stuff, that would be the place to go, because then the delta then advances out over that and buries that, and so it's preserved, for all time until it gets eroded out. So if you can explore that bottom set bed, that early stuff, and we may be sitting in it right now. I don't know. Maybe we'll find that out in the next few days. Then that's where you would look for organic things that were like died and got covered with all of that fine silt very gently, and then totally covered for a long period of time and preserved. So that would be the best place, but really any place in a delta is fair game for preservation of something. Just has to be locally in the right conditions.
So we're getting close to the end here. please put your questions into the Q&A box. Given that the cameras on earlier rovers were compromised by a sandstorm, is there a mechanism on this one to remove dust particles?
No, we don't have to worry about dust. Like Curiosity, this is nuclear powered, so the heck with dust. We can just power on through. The dust really doesn't affect the instruments too much. It gets on the lenses, but it's so dry on Mars, the dust usually falls off, and so we don't have to worry too much about dust. Everything's pretty well sealed against that. Dust is prevalent everywhere on Mars, so you pretty much expect it, and so we don't anticipate problems with that. So we don't have to worry about removing it. In fact, maybe we'll get a wind gust like we did on Spirit and Opportunity. They'll just vacuum the dust off of the rover from time to time. Who knows?
So that looks like a lot of interest in the helicopter. Why the planned flights and where does it go when not in use?
So right now it's a technology demonstration that will last only, a few weeks. So when it does the test, it flies. Well, depending on what we're doing, but most of the tests we have it return to its original location. So they'll just sit there on the ground and relay information back to the rover, and sit there overnight. It does have a ability to survive Martian nights, at least for a while. And then we'll wake up and do a test the next day. So that's why one of the reasons why we wanted to do the test with the helicopter right away was to basically to get that demonstration out of the way before we started really moving, because once we start moving, we're going to be traveling. And we don't want to just sit there and basically do tests with a helicopter. So we haven't really talked about the scenario for what if the helicopter is still functioning when we get ready to start moving, but that might become part of the plan, is to have it kind of hop along behind us or something. I don't know. It'll be interesting to see what happens.
So what type of information will be sent back immediately?
From the helicopter or the rover?
Either.
From the rover, we send it back immediately. As soon as we have the end of day overflight by a orbiting spacecraft that we use as a relay, we send as much as we can back, depending on how much downlink we have for that particular overflight. For the helicopter, a lot of the stuff gets sent back right away. It gets because we want to get all that data before something happens. And there's 2 cameras on the helicopter. There's one looking straight down. It's kind of like the Nav Cams, black and white. And then there's one that looks like 20 degrees out to the side. It's kind of a nice high-resolution color camera. So hopefully we'll get like images of the rover sitting on the surface and things like that with that one. And that one actually has the capability of being sent directly back to the Earth if necessary. So all of that data comes back as soon as we can. Very little data gets stored unless it's just very low priority stuff.
And is Perseverance the one who drives Ingenuity?
No, we basically told Ingenuity, a couple of things it wants to do, and it has onboard autonomy for, doing the flying. And so we'll tell it to do, fly up, 10 meters and translate over 10 meters and then land, and it'll do that. So it's kind of like, programming, really very functional drone is here on the Earth.
Okay. Often when paleo prospecting or doing any kind of geology on Earth, we find the best stuff just as we're about to pack up and go home. What if the best sample is discovered after 20 samples are cached?
Yeah, that's kind of a nightmare scenario. And so we have lots of arguments and discussions about how to handle that sort of thing. And it's never clearly resolved. But if it's really important, we'll just invest the resources necessary to make sure it becomes part of the cache. Even if it requires driving back to the cache site to leave that. So those are the sorts of decisions that really kind of get made in the proverbial smoke. Well, not the smoke-filled rooms in this case, because there won't be any politics or anything involved. It'll be all about what's the best science for the mission, and so we'll it would be an interesting discussion. But we've had discussions like that in the past about driving back, so I wouldn't leave that off the table.
Time for two more questions. What happens to the craft that brought the rover?
You mean the jetpack that we landed with? That basically is designed to fly off on a trajectory off to the side and fly until it runs out of fuel, so that we don't burn leave fuel all splattered all over the surface as much as possible. So it flies off and goes into a trajectory that goes over far out, several kilometers, and crashes back into the surface. So it's basically it commits suicide to further the purpose of the mission.
And there's no orbiter or anything like that.
We came in directly from interplanetary space, intercepted Mars, and almost got splattered on its windshield, but we slipped along the side and entered the atmosphere and dropped down in a chute and jetpacks.
Is the patterned ground east of the landing site found elsewhere on Mars? There are similar exposures in former Pleistocene lakes in Nevada.
Yeah, that's what's. Yeah, I thought that was kind of interesting. Yeah, we see that a lot in a lot of places, and yeah, that's one possibility. And the other possibility is, a lot of these massive sandstones, if you get on top of them, just the flexure of the surface over the years, over the millions of years, results in a lot of polygonal fractures and things, joints. So it could be any number of things. It'll depend on what the material is, and we're sitting on it, or very close to it, so we ought to be able to determine. But yeah, that's certainly one possibility, that it's a fine, muddy lake floor deposit that has been desiccated at some point. But usually those are much bigger polygons, because the desiccation is so deep and the materials are so thick. But maybe it's a thin deposit, blah, blah, blah. So that's why, again, we send field geologists out in the field to actually look at the rocks, so we can say something rather than speculate about it.
And also with us is someone who was associated with the MER Spirit and Opportunity mission as a teacher, as one of NASA's 13 only teacher-student teams. One of them was from right here in New Mexico. So Mr. Joseph Aragon would like to ask, are all STEM disciplines represented on the science team?
All
STEM disciplines.
Oh yeah, well, yeah, let's see. We've got engineers, we've got atmospheric sciences, we've certainly got a couple of geochemists. We've got now we have a field geologist. I don't know. I'm sure.
Mathematicians.
Pardon?
Mathematicians.
Yeah, well, there's a lot of people who basically started out in math and then ended up with one of the natural sciences. So yeah, I'm sure we have mathematicians there. And by the way, hello, Joe.
It's good to have so many old friends with us. Okay, good questions keep coming in. I promise. Last two. Where are the UAE and China landings going to take place compared to ours?
Yeah, the UAE is an orbiter, so it won't be landing. And that, in fact, it's in a very high orbit, but it's mainly concerned with looking at the atmosphere of Mars. So it's an orbiter. The Chinese lander at Tianwen-1 is located about 1,500 kilometers out to the northeast of where we landed, out in Utopia Planitia. And at least that's where they have said that they project to land. And so it's not going to be too far away. So between Perseverance, the Chinese lander, and Curiosity and Insight, we'll kind of have a Mars triangle on the eastern hemisphere there. Yeah, it'll be kind of interesting to see where they ultimately land.
Okay, final question. What joy. So many years of planning, dedication, expertise. What are you going to do to celebrate this successful landing?
Gee, that's a good point. There's not too much time to celebrate because we have to dive right into, you know, arguing with each other about, you know, what we're seeing and things like that. But yeah, so maybe in the next hour or so, maybe I'll have a glass of wine or something. Like, you know, it's been a long day, really.
And you are going on, the science team is going on Mars time, correct?
Yeah, we've been instructed that since, you know, we're doing all these setting up the shop type activities that are largely engineering things, that you know, the full science team really probably doesn't have a lot that we need to be there for every moment of that. So the current plan is that while some of the science team members, especially those associated with some of the instruments, will go on Mars time now. A lot of us are probably just going to drop in periodically until, you know, it syncs up with Earth time, and by that time we should be about in a position to start moving. And depending on whether things get exciting at that point, some of us will or will not be going on Mars time. So yeah, some of us yes, some of us no.
Okay. Thank you very much. And thank all of you for attending and celebrating this great event with us. We greatly appreciate it. Keep an eye on the museum website for more information, more programming, and keep thinking about Mars. Thank you.